Hello everyone. Today what we're going to do is we're going to determine the chemical formula from experimental data. You're going to probably hear this as combustion analysis. If you recall, the empirical formula is the simplest whole ratio of the atoms in a compound. And in order to obtain this formula, you need either the percentages of each of the elements involved in the compound or the masses. Now, when you find empirical formula, and here's a quick review, either you start with grams or percentages, and the first thing you want to do is convert the grams to moles. You want to change everything to moles. If it's in percentages, you assume the compound is made out of 100 grams, which basically allows you to remove the percent sign, replace it with a G for grams, and once everything's in grams, divide by their atomic masses and change them to moles. Once you change everything into moles, identify who's the lowest number of moles, divide all of them by the lowest number of moles, and you obtain hopefully a whole number. Sometimes there's a number that has a decimal where you would have to do step 5 here. And in order to convert that decimal into a whole number, you have to multiply all the numbers by a certain factor. For example, if a number ends in 0.5, you multiply by 2. If it ends in 0.33 or 0.67, you multiply by 3. 0.25, 0.75, you multiply by 4. You might even have a scenario where it ends in 0.2 or 0.4. In that case, you multiply by 5. Okay? Obviously, you would skip this if all the numbers are whole numbers. Now, the difference today is that you're not going to be given the data in grams. You're going to be given what is called a combustion analysis. It's a technique where from the compounds that are obtained, we're going to extract mathematically the grams of each of your elements in the compound that you're trying to solve. Now, here's what we're going to do. I'm going to show you, and you can always refer to this page here because this gives you a summary of what you're going to be doing. I'm actually going to walk you through this. This is a device that allows us to figure out how to do a combustion analysis. Now, if you remember, combustion is when you burn a substance in the presence of oxygen. Oxygen is a reactant. You can see us adding oxygen here, and there's a sample in this furnace being burned. Now, the sample could be just a hydrocarbon, where you have X amount of carbons, Y amount of hydrogens, and our goal is to find out what is the value of X and Y, how many carbons, how many hydrogens in the empirical formula. Well, when you burn something, when it undergoes combustion, oxygen is being used, and you form carbon dioxide and water. Now, it doesn't always have to be a hydrocarbon. It could be another compound, maybe a sugar or an alcohol, something like this. Alcohols usually have this type. But the thing is that whether it's a sugar and alcohol, if you burn these substances, you get carbon dioxide and water. These are your usual products when you have these elements. Okay, now, could there be another element in there? Sure, there could be nitrogen, sulfur, there could be another element. Now, we're going to keep it simple. We're going to keep it right now to carbon, hydrogen, and oxygen. So, let's say we were burning a hydrocarbon. Now notice, while oxygen's being pumped in here to ignite this combustion, the gases are going to be coming out this way. Now strategically, this first compartment has what is called a water absorber. So the material here is probably some polar material because water vapor is going to flow through here. And what's going to happen is, as the gases flow, water being polar is going to get captured by all of this. So all the water is going to be collected here, all the water vapor, being a polar gas. Any non-polar gas is going to keep going through here. Okay? Now, carbon dioxide is a non-polar gas. And what's going to happen over here is, as carbon dioxide is being generated all the way over here, it's going to be pumped. The water vapor gets collected in this compartment, and then the CO2 is going to be collected here. Now, if there's any other extracts, let's say other just oxygen or nitrogen or anything else, any other gases that are not absorbed in these two compartments can be collected as they go through. The key is that this compartment will give us all of the water absorbed, and we can weigh this as a mass, and this compartment will give us all the CO2. So when you're doing a combustion analysis, you're going to know how many grams you collected of water because of this compartment here on the left, and you're going to be also told how many grams you collected of carbon dioxide. Now, believe it or not, with that information, you can actually figure out the empirical formula from this data. So here's what we're going to do. Let's do a sample where we're going to do a combustion for a hydrocarbon. So here you got a combustion that contains only carbon and hydrogen. So notice it tells you collected 1.83 grams of CO2. Again, that comes from that second component. And it also tells you that you collected 0.901 grams of H2O. Now I'm going to show you a trick. I think you're going to like this. This can save you some time. All the carbon in the sample will be found in the carbon dioxide component, because carbon dioxide has the carbon element. All the hydrogen will be found in the water. So what I'm going to do is I'm going to show you how to use the 1.83 to figure out how many grams I have of carbon, and I'm going to show you how to use the 0.901 to figure out how many grams I have of hydrogen. Now, here's how you do this. I'm going to show you this from scratch. There's a concept that you've learned before called percent composition. I'm going to do the percent composition of CO2. To do the percent composition, we're going to find the molar mass of carbon dioxide. There's one carbon, two oxygens. Carbon is 12.01 from the periodic table. Oxygen is 16. When you do the math and you multiply, and then you add the mass, or the molar mass of carbon dioxide is 44.01 grams per mole. Now, if I wanted to find the percentage of carbon, and this is what I want, if I want to know the percentage of carbon in carbon dioxide, what you do is you get the part of carbon, which is the 12.01 over the total, which is 44.01. I'm not bothering putting units because they're going to cancel anyways. And when you multiply by 100, you're going to get 27.29%. That is the percentage of carbon in carbon dioxide. Now, I'm going to do the same thing for water. Okay? Water, let's do the molar mass, has HO. You got two of these, one oxygen. Multiply here by the molar mass of hydrogen, you get 2.02. Oxygen is 16. Add that up, and your molar mass is 18.02 grams per mole. So what is the percentage of hydrogen in water? It would be the part of hydrogen over the total of the compound of water times 100, and that ends up giving you 11.21%. So notice I have the percentage of hydrogen from water, and I have the percentage of carbon from CO2. Now watch how I'm going to use this data to figure out the grams of carbon and hydrogen for this problem. If you notice, 27.29% of the 1.83 grams is carbon. Mathematically, you can do this. 0.2729 times, which is what the word of is, 1.83 is going to be equal to the mass of just carbon from the 1.83. Now, when you do that, you get 0.4994. Okay? We could have just kept it at 0.499. So this is how many grams we have of carbon. So we got our first piece of data. All we need now is hydrogen. We'll do the same thing. 11.21% of the mass of the water, 0.901 grams, is going to be due to hydrogen. So, mathematically, you're going to go 0.1121 times 0.901 grams is going to equal to the mass of hydrogen in that water, and that ends up being 0.101 grams. Now, let's circle these two numbers. This is the mass of the hydrogen. This is the mass of the carbon. Now, we're going to go to the next page so we can finish this. And now we have our data. We know that we have for carbon, we got 0.4994 grams. And for hydrogen, we got 0.101 grams. Now, we're back to square one. Now we can find the empirical formula. All you got to do is divide each by their atomic mass. Your goal is to convert them to moles. So we're going to divide by 12.01 here. We're going to get 0.0416 moles. Divide this by 1.01. You're going to get 0.1 moles. Then the next step is divide by the lowest, which happens to be this one up here. So you're going to divide both of them by 0.0416. This is going to give you a 1. And this one, and this is going to be very interesting, this one gives you a 2.4. Now earlier, I don't know if you remember when I mentioned this, if something ends in 0.4 or 0.2, we could use the same rule. The rule is to multiply by 5 to get a whole number. Okay? So what we're going to do here is we're going to multiply both of these, because remember, what you do to one, you do to both. We're going to multiply them both by 4. So when you multiply the carbon by 5, excuse me. I apologize for that. I wrote it correctly over here. You're going to multiply by 5. So when you do this, there's a 1 here, so there are 5 carbons. And when you multiply 2.4 times 5, you're going to get a 12 here. So you're going to end up getting 5 carbons. So it'll be C5, and then 12 hydrogens, H12. And this will be your empirical formula. Okay, so again, if it ends in 0.4 or 0.2, you don't see this one often. You multiply by 5, and that's how we got to C5H12 as the final answer. Okay? All right, so this one's a little bit more complicated. The reason is this is not a hydrocarbon. This one has 3 elements. Okay? However, they also tell you the mass of the entire sample. You'll see the importance of that in just a moment. So here's what we're going to do. If you recall, let's break down the data. Well, here we got, for CO2, we have 2.445 grams. For water, we have 0.6003 grams. Now remember, from the CO2, we can find how much carbon we have, and from the water, we can find out how much hydrogen we have. So we're going to take a shortcut because we already did the percent composition for carbon in CO2 and for hydrogen in H2O. So if you remember, I told you that 27.29% of the CO2, which is 2.445, is going to be carbon. When you do the math, you're going to get 0.2729 times 2.445, and that's going to give us our mass of carbon. Okay, I end up getting 0.6672 grams. So there's our carbon. And then if you also recall, we said 11.21% of the water, which is 0.6003, is going to be our hydrogen. So when we do the math, 0.1121 times 0.6003, and of course those are, everything here is in grams, that when we do the math ends up being 0.06729 grams of hydrogen. So we have our grams of carbon, we got our grams of hydrogen, but we're missing one piece. This also has oxygen. So here's what you're going to do. Add the two numbers that we just got together. Add the carbon, 0.6672 grams, and add it with the hydrogen, 0.06729 grams. When you add these numbers, you get 0.7345 grams. Now, I want you to realize that that number is the carbon and the hydrogen together. Do you remember that in the beginning, you have the mass of the entire sample? So look what you're going to do. If you get the mass of the entire sample, 0.8233, minus, so we're going to subtract it with the number that we just got. Remember, this number here is the C and the H together. When you subtract the sample minus the C and the H together, the difference, which is 0.0888, is going to be your grams of oxygen. So now, not only do we have the carbon, the hydrogen, and the oxygen, and here's something interesting. If you add these three numbers in red, they're supposed to add up to the mass of the entire sample, and they do. Okay? So now we have everything we need, and we can go back to step one, which is to find the empirical formula. The difficult part here is to find the mass of each component. Once you have that, finding empirical formula is actually pretty easy. So here's what we're going to do. Let's write the data down that we just obtained. Okay? So we have three elements, C, H, and O. And our carbon, we had figured out it was 0.6672 grams. Our H was 0.06729 grams. And then we just found our oxygen to be 0.0888 grams. Again, the first thing you're going to do is divide by their atomic masses. So we'll divide here by 12.01, 1.01, and 16. And the purpose is to convert everything to moles. So carbon is 0.0556. Hydrogen is 0.0666. And oxygen is 0.00555. So once you convert to moles, find out who's the lowest. It's the third number. And then you're going to divide all of them by the lowest. So let's set it up over here. Just like this. Okay, so for carbon, when you do the math, you get, basically, it rounds to a 10. You get a nice even number there. The second gives you a 12, and the third gives you a 1. Now, the nice thing about this is that these three numbers are whole numbers. We don't have to do any additional steps. These numbers are our subscripts. So we pretty much have our answer. So according to the data, there are 10 carbons, 12 hydrogens, and just 1 oxygen. Now again, remember, we don't need to write a 1, so I'll erase it. And this will be the empirical formula from the combustion analysis information. Okay? All right, so here are 2 practice problems that I have for you. The first one is just a regular hydrocarbon, so it only consists of C and H. So your job is to find out the value of C and the value of H. And the second problem is similar to the one we just did, where it has 3 elements, so you need to find the value of C, H, and the O. All right? So I want you to perform these, and then these we can check them in class together. Okay?